In this section, we will see another method how to compute the inverse matrix using minors and cofactors, similarly as we were computing determinant. Remember, if we have a matrix, a square matrix, n by n, then we can choose one particular row, say ith row, and we can choose jth column, where I and j are between 1 and n. We delete this row and this column, and what remains is a small matrix, which is again a square matrix. We can compute the determinant of this, and we call it minor, denoted as capital M sub ij. I denotes the row that was deleted from the original matrix, and j denotes the column that was deleted. It is not an element on position I and j. This is not something like matrix M with element on position ij. No, this is the number, this is the determinant of this smaller matrix. And then, if we multiply this by minus 1 to the power of I plus j, then this is another important number, which is called cofactor, and it also depends on I and j, the row and column that was deleted from the original matrix. Well, and you may remember that the determinant of this square matrix can be computed and can be defined using the expansion along a given row or a given column in the form that this is the sum of A sub ij times capital A sub ij. And now we can either fix any I and sum over j, which corresponds to computing the determinant along a given row, or alternatively, we can fix j and sum over I, which means that we expand the determinant along a given row. Vice versa. If we fix j, then we fix the column, and when we fix I, we fix the row. So when I runs, then I is here, and it runs from 1 to n, and we expand along a given column. And now, using these objects like minors and cofactors, we can write an algorithm how to compute the inverse matrix. Please don't confuse capital A sub ij and small a sub ij. Small a, ij are entries in the original matrix, capital I. But these are not the entries of the matrix capital I. These are the cofactors evaluated by this way using the minors, which are in turn evaluated from the entries of the matrix capital A. Well, and the theorem goes that the matrix A inverse can be written as 1 over determinant of the matrix A times matrix that is composed of the cofactors, namely A11, A12, up to A1n, A21, A22, up to A2n, up to AN1, AN2, up to ANn, and transpose of that. That's all. It is easy to show that this is indeed the inverse to A. Well, first we have seen here some scalar coefficient. So for this expression to exist, we want determinant to be different from 0. This is actually a very important property. The inverse matrix exists to a given matrix A under two conditions. A must be a square matrix, n by n, and the determinant must be non-zero. It is easy to show that this is indeed the inverse. Well, if we multiply the original matrix A with this expression, then this is a matrix, and its entries look like that. Say, let's start with 1, 1. That means we take the matrix A, and then we take this object, which is 1 over determinant of A times this matrix composed of the cofactors and transpose of that. So one particular entry of this product is up to this scalar factor, is the scalar product of one row from A and one column from this transpose, which is equivalent to one row of this before transposing. You see, column of this is equivalent to row of this without the transpose. So if we write just the matrix A, and if we just write just to the right, not multiplication, just this matrix. Or possibly larger. The size of the matrix is not important. So we want to consider one entry of this product, which should be the identity matrix, and which should be something like that. That means if these two indices are the same, we expect to get 1, and if they differ, we expect to get 0. So let's start with the first row and the first column. If we consider the first row here and the first, okay, let's start with the position 1, 1. So the first row here and the first column here, which corresponds to the first row here. But this is sum of the products of the entries, small a times capital A, and this is exactly the determinant of the matrix. And when we divide by the determinant, we get indeed 1. That's good. And this is true not just entry 1, 1, also for the entry 2, 2, because then the second row here times the second row here is again the determinant, and this times we sum over j. Well, and this is true for any I. So any row here, when multiplied with the corresponding row here, gives the determinant, and we divide by determinant, we get 0. So we have zeros on the diagonal of this product. Well, and now we want to show that if they differ, we get 0. So let's start with I is 2 and j is 1. That means, say, we want the second row from this matrix and the first row from this one. This also resembles evaluating the determinant. But of which matrix? These numbers, the cofactors, which come from the minus, which come from deleting one row and one column, if we look at the cofactors on the first row, they are computed from the matrix when we delete the first row. So these numbers are independent of the first row of the matrix. So we can consider a matrix, if it is independent of the first row, we could replace the first row with a copy of the second row. Say, if we have a matrix 2, 3, 5, 6, then we write 5, 6, 5, 6. We just replace the first row with a copy of the second row, and leaving the second row unchanged, untouched. Changing the first row does not change this matrix of the does not change the first row of this matrix consisting of cofactors. But then, if we replace the first row with the second row, then this product is the determinant of a matrix where we have identical rows. And the determinant of such a matrix is equal to 0. And this is true in each case when the number of row here and the number of row here differ. So this completes the proof that this way we get indeed the identity matrix. So this way we see that this is indeed the inverse to A. Okay, let us illustrate this for our previous method, for our previous matrix. So once again, we have the matrix capital A being 2, 3, 1, 1. Let's compute the 4 cofactors. Capital A, 1, 1. We cancel the first row and the first column. And we are left with this small matrix, and its determinant is 1. For the cofactor capital A, 1, 2, we cancel the first row and the second column, so we get the number in position here. We get the determinant of this, which is 1, but we must multiply by -1, because we are in the position where we have minus in this checkerboard structure. The cofactor A to 1 is found this way. We cancel row number 2, column number 1, and we consider this as a determinant, which is 3, and we multiply by minus, so we have -3. And finally, the cofactor capital A to 2, we cancel the second row, the second column, and the determinant of this is 2. So, using this algorithm, we find that the inverse is 1 over determinant of A. Yes, we prepare the determinant of A. 2, 3, 1, 1. Which is 2 minus 3, which is -1. So we have, and here we have the cofactors A11, A12, A21, A22, and transpose of that. So we have 1 over, this is too thin, 1 over -1 times A11 is 1, A12 is -1, A21 is -3, and A22 is 2, and transpose of that. So when multiplying by -1, we have -1 and -2 on the minor diagonal. And when we multiply by -1, these two entries become positive, and when we transpose, we should swap their position. So we have 3 and 1 here. And now we can compare this result with the previous one. -1, 3, 1, -2. Yes, this is the same. So this was another way how to compute the inverse matrix using cofactors. And this works not just for a 2x2 matrix, it works for any size matrix.